in August 2003, 56% of employed adults in the United States reported that basic mathematical skills were critical or very important to their job. The supervisor of the job placement office at a four-year college thinks that the percentage has increased due to increased use of technology in the workplace. He takes a random sample of 480 employed adults and finds that 297 of them feel that basic mathematical skills are critical or very important to their job. Is there sufficient evidence to conclude that the percentage of employed adults who feel that basic skills are critical or very important, basic mathematical skills are critical or very important to their job has increased at the alpha equals to 0.05 level of significance? Okay, so alpha is given. That's the probability of making a type 1 error, right? Remember, a type 1 error is the case where you reject the null hypothesis when you shouldn't have rejected, right? Falsely rejecting the null hypothesis, rejecting the null hypothesis when the null hypothesis is true. Okay, so we can tell that this is a chapter 10 question 10.2, which is on population proportions. This is 10.2, and this is number 19. Okay, so you always have to begin by thinking about your null hypothesis. And our null hypothesis in this case is going to be the case that everything is the same, nothing has changed. So what would it be? P equals 0.56%, right? These problems are really hard because you kind of start off with a blank page, like what do I do? Where do I start? So we always start by writing down our null and our alternative hypothesis. Our null hypothesis written like that is always going to be either a mu, a p, or a standard deviation there, sigma, and it's always going to have an equal sign, and it's always going to be equal to some number. Okay? Now that number is something that is going to be provided for you in the word problem in one way or another. In this case, 56% is the proportion that was true back in 2003. So we want to know, 13 years later, is it different? Is it higher? Is it lower? That's what we want to find out. So the null hypothesis is that nothing has changed, everything is the same, it is no different. And now the alternative hypothesis is going to be P 0.56, and there's only going to be one of three things that we deal with in this class. This guy is either going to be a not equal to situation, or it's going to be a less than or equal to, or it's going to be a greater than. So it's going to be a not equal to, a less than, or a greater than. It's only going to be one of those three. You have to decide based on the word problem. So which of the three is it? It says, is there sufficient evidence to conclude that the percentage of employed adults who feel basic mathematical skills are critical to and important to their job has increased? Right? Is there enough evidence to show that it is bigger? So it's this last one, right? So that's the one we're going to be working with. This guy is going to be, is there enough evidence to support that P is actually bigger now? Good? Questions, comments, issues? No? 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 Okay, so now where do we go from here? So what we're going to do is we are going to assume this is true. Assume this is true, and then based on the assumption that that's true, we're going to take our sample data that they've given us and assess the plausibility, the likelihood of getting such an example under this assumption. Got it? Okay, so what I'm about to do is not part of the work that you would need to show, like say on a test question. I want to just kind of do like some side work here to give you some background on why what we're about to do or how it works out. So I'm going to go over here and I'm going to look at my test. Well, actually, let's just write down our sample stuff. So the next thing you should write down is your sample information. Sample information. And the sample information is that we took a sample of size n equals to 480. And x, the number of values that were successful, was 297. So therefore, our p hat, our sample proportion, is 297 over 480, which turns into
61875.
61. So 0.61 what?
875.
875. Okay, so we can go to 4 decimal places and round that to 88. So our p hat is 0.6188. Okay, so we got a sample result of 61.88%, but we are under the assumption that the null hypothesis of the entire population is this, right? So again, let me do a little bit of side work here to show where we're heading with this. So remember that back in chapter 8, we knew the following. So recall back in chapter 8, that when we have a population, this is all Americans. Right, so the entire U.S., the entire population of all Americans. Maybe it's true, this was back in 2006, 2003 it was true. So we're going to assume it's also true in 2016. We're assuming P equal to 0.56 is the proportion of Americans who feel that their job does require some basic mathematical skills, right? So we're assuming this to be true. And if we assume that to be true, from chapter 8 we know that if we take samples of a size n equals to 480, right? So one sample could be that we surveyed 480 people and we asked them a yes or no question. Is it true that your job requires some basic mathematical skills? Nope, I don't need it. Don't need it. Nope, I don't. No, I don't. Yes, 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 no, yes. Right? That's what's happening. Yes, no, no, yes, 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 no, no, no. So we're getting a bunch of results. Maybe in this sample, maybe only 208 people said yes. So we would get a sample proportion, p hat, of 208 divided by 480. Right? What's that? I should probably get my calculator too.
0.43.
Like, okay, I'm just going to go to 0.43, so 43%. Here is one sample. In this sample, I got 43%. Right? Then we do it again. We take another sample. Yes, yes, no, yes, no, no, yes, yes, da 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 da. Maybe in this sample, maybe it was 285 people that said yes, we do use basic mathematical skills. 285 out of 480.
0.5938.
598, you said? So close to 60. Okay, so then we do that over and over and over and over, hundreds and thousands of times, and then we know that if we graph these guys, they turn into a normal distribution. Under certain conditions. What are the conditions?
The sample size is big enough.
NPQ has to be greater than or equal to 10, which in this case is going to be 480 times 0.56 times 0.44, and that is going to be greater than 10. So we're going to be okay there. And then the other condition is that our sample size must be smaller than 5% of the population. Otherwise, we get into a conditional probability situation that we want to avoid. So we want to say that 480 is less than 5% of all Americans. Yes, that is going to be less than 5% of all Americans, so we're good. We've satisfied both conditions. Okay, so this guy is going to be a normal distribution, normal sampling distribution. We know that the mean of this little p hat is equal to the proportion from where the population came from, 0.56. We know that each one of these little guys here is a little p hat. Every little dot on here represents the sample proportion where the sample size is 480 and it comes from that population of all Americans, right? Okay. The standard deviation of this p hat is equal to p times q divided by n, p times q divided by n, and then we take the square root of all that. So 0.56 times 0.44 divided by 480, square root of that whole thing. 0.56 times 0.44 divided by 480 to the 0.5 power. I get 0.2266. 2266? Oh, there's an extra zero in there. 0.02266 Okay, so that's the normal distribution. And now what's happening is that we assume this to be true. We know that when this is true, or we're assuming it's true, that this happens. But now we went out and took one sample, and that one sample resulted in 297, right? So our sample is in here. Our sample from this word problem is right in here, and it says, you know, they went out and took a survey. It was a yes, it was a no, no, a yes, yes, no, yes, da 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 da. In this one sample, we found 297 people indicated that yes, they do use basic mathematical skills in their work. And so that means that the sample proportion we're dealing with is 297 over 480, which is equal to 0.297 divided by 480, 6188. 6188. So that guy is somewhere right in here, right? That represents one of the dots right in here. It's right in here at 0.6188. Everyone's with me so far? Okay, so under that assumption, all of this is true, and now what we want to ask ourselves is, if that is true, what is the likelihood of getting this kind of a sample? Well, that's exactly what this shape over here is telling us, right? Remember, the shape above the horizontal line describes the likelihood that something would happen. So I want to know what's the probability that that would happen, or something more extreme. So I want to know that right there, the area to the right of that one. How do I know it's that one? It's guided by two things. One, it's always that or more extreme. That's what we always want to know. But also it's guided back by our alternative hypothesis. Our alternative hypothesis being that it's greater. Because I see that it's greater, then I know that I'm looking for that or bigger. That's why I'm over here in the greater, right? I mean, if you think about it, if I'm trying to find evidence that it's bigger, and I go out and take my sample, and my sample is smaller, well, then obviously there's no evidence. I'm assuming it's bigger than 56, and I take a sample and the result is 53. Well, I have absolutely no evidence that it's bigger. But maybe if my sample is bigger, then you might be convinced, like, oh, okay, there might be a case there. But maybe if it's just a little bit bigger, like maybe 56.1%, like, you know, a little bit of variability, that's not that big. But what if I took a sample and it was way bigger, it was like 93% from our sample, then maybe you'd be a little bit more convinced, right? So we want to know exactly, numerically, how likely is it that this result would happen under that assumption. So we know that that's going to be normal CDF from here to infinity with this mean and this standard deviation. So the probability, go back to blank. So the probability that p hat is greater than 0.6188 is equal to normal CDF of 0.6188 up to infinity with a mean of 0.56 and a standard deviation of 0.02266. So let's find that out. Normal CDF of 0.6188, comma, infinity, comma, 0.56, comma, 0.02266. So I'm getting 0.0047, 0.0404731. So whatever else got? Yeah, good. Okay. As a percentage, that's really small, right? This is equal to 0.4731%. it's a little bit less than 1/2 of 1%, that's pretty small, isn't it?
Yeah.
That's a highly unlikely result. Okay, so going back to our additional here, we start off by assuming this is true, and we're trying to see if there's enough evidence to conclude that this one is true. So if we assume that's true, we look at our sample, and we figure out that the likelihood of getting an example like this one under that assumption is pretty small. The likelihood is less than 1/2 of 1%. So when the likelihood is small, very small, we reject the null hypothesis in favor of the alternative, right? It's unlikely that the population proportion really is 0.56. It's more likely that it is a little bit bigger because our sample result was a little bit bigger. Exactly. Okay? All right, now we need to formalize a little bit more with this. We don't want to do all that work every time, right? We don't want to go over here, every single word problem, and come back over here and do this. Now, I will do it a few times to make sure people get this underlying concept, but you don't want to have to do all this work every time, right? So we have a nice formula that this chapter will give you that helps you figure out this probability right here. Okay, remember that the way they do it in this book is that they don't take advantage of our calculator function of being able to choose your mean and your standard deviation. They don't find this directly, right? What does the book do? It takes you over to the standard normal distribution. It finds out what this would be proportionally equal to in a standard normal distribution, and then they go to the tables and they find the answer in their table, right? So we want to take advantage of that process of finding the one that's proportionally equivalent because we want to use that formula. That's it. So after you get that value that's proportionally equivalent in the standard normal distribution, then we can go back and use our normal CDF and then just use the 0 for the mean and the standard deviation as 1, and then get our probability from there. The reason we want to do that is because we want to use their formulas and rely on their formulas. If you recall, do I have it? The formula sheet you'll be given is this one. Here is the formula sheet that you'll be given on the test. It's the one in the back of your book. And so there are the formulas for chapter 10. So the one we need right now is the one in the left corner over there. It says Z naught is equal to P hat minus P naught divided by the square root of P naught times 1 minus P naught all over N, and so on and so forth. Okay. What is this piece of naught thing happening there? Well, that goes back to this. In order to reduce confusion, well, hopefully reduce confusion, what we do is that we refer to this one, this P, as P sub 0, indicating that it's the assumption, the value of P under the assumption of the null hypothesis. Okay? All right, so let me continue back to this thing. All right, so what we're going to do, if we didn't have this awesome calculator and we wanted to solve it by the tables or do it the way the book does it, once they get to this stage right here, they got to transfer this to the standard normal distribution. Okay, so we're going to have a nice standard normal distribution. Standard normal, which means these are z values. And then here we call this mu sub 0 and sigma equals to 1. Right? That's always the standard normal distribution. And what we want to do is we want to figure out which value on here is proportionally equivalent. That's going to give you the proportionally equivalent area. And remember that to do that, we figure out the multiples of the standard deviation, right? All normal distributions are proportionally equivalent as multiples of the standard deviations of their own distributions. So like if I went exactly 2 standard deviations here, and I went exactly 2 standard deviations here, they will both trap the same area under the normal curve. Good? Okay, so we find the z-score. That's exactly what the z-score does. The z-score tells me which z value here is proportionally equivalent to this p-hat value. So z-scores are, if you remember, z-scores are x minus mu over sigma. So we're going to be working with this guy, and we want to find its z-score. So in our case, well, we don't have an x, we have a p hat. Right? And then, okay, well, we don't have a mu, we have a mu sub p hat. We have a p hat minus mu sub p hat divided by sigma sub p hat. That's what we have. And that's how we get the z-score of that guy. So for our case, it'll be 0.6188 minus 0.56 divided by this thing here, which is equal to 0. I'm going to write this whole thing out for a second so we can see the formula. 56, 0.44 all over 480, square root of that whole thing, which we know is 0.6188 minus 0.56 divided by 0.56. Oh, we know that that thing is really equal to 0.02266. Now we can get an actual value. 0.6188 minus 0.56 divided by 0.02266. I'm getting 2.5948. 2.5949. Pretty close to 2.6. Good? Questions, comments, issues? Okay, so this is telling me that this number is about 2.6 standard deviations to the right of its mean. So if I go over here 2.6 standard deviations to the right of its mean, I will find a value that will give me an area proportionally equivalent to that one. Well, the great thing about the standard normal distribution is that it's centered at 0 and the sigma is 1. So when I go 2.5949 standard deviations to the right of it, it's really that exact same value because the sigma is 1. Got it? So here we're saying that if I multiply this value of sigma p hat times 0.02, times 2.5949, that I will get to that number. Right? That distance right there is that. The mean plus this gets you to that. 2.5949 times its sigma gets you to that point. So over here, I need to go 2.5949 times this sigma to get to that point. But luckily, in the standard normal distribution, the sigma is 1. So it's just that number, 2.5949. That's one of the nice things about the standard normal distribution. So if I go over here to 2.5949 and I find the area to the right of that value in the standard normal distribution, then that will let me know the area of this blue region. Right? So with our calculators now, we can find this area by doing this. So we're going to say that this area right here in red is equal to the probability, it's going to be long. So the probability that z is greater than 2.5949 is equal to normal CDF. Run out of space. Is going to be equal to normal CDF from 2.5949 up through positive infinity with a mean of 0 and a standard deviation of 1. Right, that equals that. That's this area right in here. And I know that when I do it, it's going to be really close to this. 0.004731. Good? Good? Sort of, kind of, maybe? Okay, so now let's look at the formula that they've given you for the test statistic. Test statistic. The test statistic is Z naught equals to P hat minus P naught all over P naught 1 minus P naught all over N square root of that. Okay? This formula right here, this is the formula that you're going to have to work with. So everything I did on the board here, here's the good news. You don't have to do any of this for this chapter. I'm giving you the background. All of this was to show you where this little guy came from. That's all. Okay? I'll go back to the other board and I'll show you what you actually have to write for this question. Hopefully this was just helpful and you see where this formula comes from, because this formula is exactly this guy right here. Right? It is P hat, that's our sample proportion, P hat. This is the population proportion under the null hypothesis, which we call P sub 0. P sub naught, indicating that it's from the null hypothesis. And then we got the null hypothesis P times its Q, which is 1 minus P, divided by N, which is this guy, and then the square root of the whole thing. So this little formula tells you this guy, Z sub naught, the Z value under the null hypothesis that will give you the area that you're looking for. Let's take a minute and pause there. What do you think? Questions? No? Good? Okay, so let's get back to the original question and I'll show you what you need to write down. Okay, so all of this was to see where that formula came from. So back to our original question, this is what I would expect you to see, to actually write down on your test. You're given that word problem, you got to start by writing down the null hypothesis and the alternative hypothesis. Then you got to get your sample information. So that sample information is sometimes just flat out given to you, and sometimes it's just a big collection of numbers and you got to use your calculator to find the mean and standard deviation and all that, so you churn out the values that you need. Next, you got to find your test statistic. Test statistic. And that's where the formula comes in. We have our formula is just given as P hat minus P naught all over P naught, 1 minus P naught all over N, square root of that whole thing. And like I said, this guy right here is what we refer to as P naught, because it is the P under the assumption of the null hypothesis, and that's what they're referring to right here. So this one's P naught, P naught, P naught. And this one is P hat, which is this guy right here, P hat. It's our sample proportion. Okay, so you can either write it down or not. This is given to you on your formula, so you don't have to write it down. It's be on your formula. So then you find your Z value. Z naught is equal to, and then you write it down, 0.6188 minus P naught, which is 0.56, divided by 0.56 times 0, well, let's go with 1 minus 0.56, divided by 480, square root of that whole thing. Z naught is going to be 2.5949. Okay, so you write that down, you found your Z value. What does this mean? This means that it's a Z value, so I know it's a normal distribution. This is the value that's going to give me the area that I need to be able to determine if I have enough evidence to support the alternative hypothesis. Okay, so now I can draw my standard normal distribution. And then these are Z values. Mean is 0, sigma is 1. And I know that here is my 2.5949. It's exactly what we did a minute ago. So there's that area over there. And now I need to find that area. So now the probability that Z naught is greater than 2.5949 is equal to normal CDF from 2.5949 comma infinity comma 0 comma 1, and that's where we say that it's 0.004 something. 47?
48.
48? What was the other one? 4748, where do you go? 4731. Okay, so far we're good? Okay, so we found our test statistic. We find the probability of getting such a result, or more extreme. We're guided to know that it's that way because of this thing. That's how we know that way. And that's why this is called the right tail test, right? To the right. So we call this one the right tail test. Good, good. This is a good place to remind you guys, by the way, that I know technology is awesome. I embrace technology, but I think that there is a point where there's such a thing as too much. So there's some awesome things some of your calculators can do that you're not allowed to do in this class. So I do need this work. I'm okay. I embrace using it to find this because it's just a replacement of using the table. So that's dumb. But all the other things that it can do, we don't use some of those things. In particular, some of you guys might know that there is a way of testing this a little bit more automatically with your calculator. And you're fine to do that if you want to double check your work or something, but I don't really accept that as an answer on the test. Just like in confidence intervals, there's a nice easy way of just pushing a couple buttons and it gives you it, the answer, and I don't accept that either. So we only do the calculator stuff that we do in class, and if there's something else that you want to potentially use, then come talk to me and ask me if that's allowed on a test. Okay? I just think that it's too easy for people to get the right answer without really knowing what the hell is happening when it's just asking you, to type in like 4 or 5 different numbers in the right places, and then it just gives you the answer. So that's why we don't use it. Okay? All right. Anyway, so now that we find this, now it's time to make our conclusion. What we have found is what we call the p-value. The p-value is the probability of getting this kind of a result under the assumption that the null hypothesis is true. Okay. This is what we call the p-value. P-value. So the p-value is this. So our conclusion is this. If the p-value is less than alpha, less than alpha, then we reject the null hypothesis. In favor of the alternative. In favor of the alternative. That's one thing. On the other hand, if the p-value is not less than alpha, then we say, then we fail to reject the null hypothesis. So that's the little conclusion that we're going to go under. So, how small is small enough? Well, it's not really up to you in these word problems. They give you the alpha value. So in this particular word problem, if you recall, the alpha value was what? 1 point. In this particular case, the alpha value was 5%. This is less than 5%, right? So it's this one. If the p-value is less than alpha, for us, alpha was 5%. 0.05. In this particular example, alpha was equal to 0. Since this is less than that, then we reject the null hypothesis in favor of the alternative. So we do have enough evidence to statistically support the idea that the proportion today in 2016 is greater than 56%. And that's it. So this board is the writing you would do. That board over there, what we did a little bit ago, that's just to support this idea of where this formula came from, right? But as we move forward, we want to rely more and more on their formulas. In this chapter, I will continue to kind of draw back to where that formula came from, because I think it's important to know where that formula comes from. But starting in the next chapter, it becomes really messy. So we'll do less of the, showing you where the formula came from and just kind of relying on this test statistic formula that they give you. Okay? Good. Questions, comments, issues? No? Okay, now let's do one from the next chapter. It's the exact same process, the exact same idea of hypothesis testing, except now we're going to be working with population means. So let's do... about energy consumption? Number 20. So this is number 20 on chapter 10, section 3, energy consumption. In 2001, the mean household expenditure of energy was $1,493, according to data obtained from the U.S. Energy Information Administration. An economist wanted to know whether this amount has changed significantly from its 2001 level. In a random sample of 31 households, he found that the mean expenditure in 2001 dollars, meaning that they've adjusted for inflation, for energy during the most recent year was $1,618, with standard deviation of $321. Construct a 95% confidence interval about the population mean energy expenditure. Oh, this is a confidence interval. I want to stick to hypothesis testing for a little bit. How about conduct an appropriate test to determine, okay, that one. How about TVolics? According to the American, can you see it? There it is. According to the American Time Use Survey, the typical American spends 154.8 minutes or 2.58 hours per day watching television. Do internet users spend less time each day watching television? A survey of 50 internet users results in a mean time watching television per day of 128.7 minutes with a standard deviation of 46.5 minutes. Conduct the appropriate test to determine if internet users spend less time watching television at the alpha equals to 0.05 level of significance. Okay. So where do we start? Well, first of all, you got to try and read the question and figure out whether they're talking about means, proportions, or standard deviations. And so they're talking about means, right? The mean amount of time spent watching television. Okay? And we're focusing on the internet users. I don't know what that definition is. Who's an internet user? Who's not an internet user these days? I don't know. But they've defined someone to be an internet user sometime. And we want to work with them. So the first thing you have to do is think about your null hypothesis versus your alternative hypothesis. And as you said, we're working with mean. So the mean is going to be equal to something versus the alternative hypothesis, where the mean is either not equal to, less than, or greater than some number. And that same number has to apply to both of them in this case. So what is that number? $154.8. 154.8. Why not the other number? Why not the 128? Because that's the sample data, right? The null hypothesis is the boring hypothesis. The boring hypothesis is that the internet users spend the exact same amount of time watching television as the non-internet users, whatever that is. I don't know, maybe people that spend more than an hour on the internet each day are internet users, maybe. So the alternative hypothesis is that mu is what? Less than, greater than, not equal to? Less. Okay. Conduct the appropriate to determine if internet users spend less time watching television. So that's what we think. Is there enough evidence to indicate that this is true? Okay, so begin by stating your null and alternative hypothesis. That's always step one. Step two, write down your sample information. Sample info. And that information is going to be that we took out a survey, n was equal to 50. We know that x bar, the sample mean, was 128.7. And we know that the sample standard deviation, s, is equal to sample standard 46.5. Okay, so we wrote down our sample information. And now next, I'm going to go over to the other board and talk about some background information to show you where the equation comes from that we're about to use. Okay, so back to this guy over here. This guy. Just go here. Okay, so back from chapter 8 again, we know that if we have, well, actually I guess this was chapter 9. We know that if we have some sort of population that is normal, we know that, well, not necessarily normal, it could be some sort of distribution, so there's some population distribution. Maybe it's normal, maybe it's not, but it's got some sort of mean, some sort of sigma. We know that if we take samples of size, n equal to, okay, well let's work with this data, n was equal to 50. We are going to assume under the null hypothesis that mu is equal to 154.8. What do I want to do here? And what about the standard deviation, sigma? We're going to make the assumption that this guy is equal to 46.5. Right? And we're assuming that's true because it comes from the sample. And then this is our null hypothesis. Okay, so we know that if we have that kind of a situation and we take samples, then when we take sample values of size 50, every one of these sample values from this population is going to give me different results. So the first one might have a sample mean of 150.8. The next one might have a sample mean of 162.7, and so on and so forth, right? So this is like 50 people are surveyed. Maybe, maybe one of them said, I spent 140 hours. Another one says, I spent 117. Another one says, I spent 2 hours. Another one says, I spent 408 hours. Right? So we take 50 of these guys, divide by 50, and that's how we get our sample mean. And then that sample mean is going to vary from every sample, or there's going to be some variability between those samples. Right? So this one might be 162. Okay, we know from our previous work that if we do this over and over and over and over again, and we graph all these x bars, over here, over there, we get some sort of a distribution that is normal. And this guy is equal to the mean of that guy, 1, so this is x bar. This is mu sub x bar equals to 154.8, and sigma sub x bar is equal to that one divided by square root of n, right, in this case 50. So it's going to be 46.5 divided by the square root of 50. And what do we get in that case? 50 to the 0.5 power, and 46.5 divided by that guy. I get 6.5661. 6.5761. Everyone's with me so far? Remember, oh, little mistake here. This is going to be x bars. Right? Every one of these little dots represents the mean that comes from a sample of size 50 from that population. And we're guaranteed this is normal as long as one of two conditions is satisfied, right? We don't need this. This could be any distribution. But, however, if it is a normal distribution, right, this will work. Works if this parent distribution, the parent distribution from where the samples came from, distribution is normal. If we're guaranteed that that's normal, then we're going to guarantee that this works out. That's one way. The other way is that, well, if we don't know that that's normal, then as long as the sample size is greater than 50, so if n is, greater than 30, we're okay. So if n is greater than 30, we're okay. Or, this is an or statement, you don't have to have both, one or the other. So, or if you know that the parent distribution is normal, then everything is okay. All right, so now what we have is a particular sample value. That sample value is 128.7. So we are told that there is some sample, one of our samples over here, for us, our sample. Sorry. Our sample had x bar equal to 128.7. So that's a dot right here. Here it is, 128.7. I want to know this. I want to know the likelihood that we would get that over there. One problem that we have to deal with, though. We assume this to be true, right? But then this guy was not given to us. We have no assumption for it. The best thing we could do is go with our sample information. S was equal to 46.5. And that's what we used here, right? This was a guess using our sample. Guess from sample. Therefore, what happens when you use a guess from our sample? It's no longer normal, it's a t distribution. With how many degrees of freedom? N minus 1. So in this case, 49. Okay? Because we're using this guy right there, it's got to be a t distribution. Everything else is basically the same. Okay, but now we really have to use their formula, or the other process, because most calculators don't allow you to calculate this directly anymore. We're going to have to apply to the standard t distribution. We're going to have to figure out proportionally what is the value in the standard t distribution that will give us that area right there. So we need to find kind of like the z value, but you know it's we standardize it. That process is called standardizing it. So we need to find this distance right there. So it's the difference between these two, and then divided by the standard deviation. Right? We called it the z-score, but in this case, it's no longer going to be a z, it's going to be a t value. So we're going to go this way. We're going to take it over to the standard t distribution. With degrees of freedom equal to 49. But because it's a standard one, I know the mean is 0, the sigma is 1. Okay? And then every one of these little values is a t value. So we don't call this as the z-score anymore, we call it a t-score. I know, the notation is crazy in this statistics. There's just so many things out there, little subscripts, and subscript of a subscript. Okay, so now we call it a t-score, but it's going to be the same formula. It's going to be x minus the mean divided by sigma, right? But okay, in this case, we don't have an x, we have an x bar. And then we don't have a mu, we have a mu sub x bar. And then we have an x sub x bar, right? Because we're working with this distribution right here. And that'll give us the t-score that we need. So in our case, we have 128.7 minus this thing, 154.8, divided by this thing, which was 46.5 divided by the square root of 50. Square root of 50. And we know that that's 128.7 minus 154.8 all over this thing, which we said was 6.5761. Okay. So that's the answer there. 128.7 minus 154.8 divided by 6.5761. This is negative 3.969. Okay. So this is the value here. So I know that if I go to my standard normal distribution and I find this value and I find this area here is going to be proportionally equivalent to that one. That's how I can find the likelihood of getting such a result by going over here. Okay? Good? Questions? Okay, and so how do we find that right there? That's going to be the probability that t is less, remember these are t values now, the probability that t is less than negative 3.969. Did I miss that?
It's 469.
Oh,
Oh, no, I got it wrong.
oh, okay. Then there's going to be TCDF from negative infinity up through negative 3.969. And remember, your calculator doesn't even ask you for the mean and standard deviation anymore, because your calculators only work with standard t distributions, and all it asks for next is degrees of freedom. Okay, let's type that in. So negative infinity,
622.
6 to 2?
No, 2.7, 622.
Okay, here, let me almost done. Wait, I'm getting some, 1.177a is what I got.
Yeah, me too.
Okay, okay. And remember, that's that little times 10 to the power of negative 4. So I'm getting 1.1778. And then there's that e negative 4 like that on your calculator. This represents times 10 to the negative 4. So this is really equal to 0. We move the decimal space 4 spaces that way. You're going to get 1, 2, 3 zeros, then a 11778. Like that. 1, 2, 3, 4 spaces that way. So it's actually really small. Really, really small. Okay, so the probability that we would get such a result under this assumption is actually pretty small. It's like a little bit less than 2/100ths of 1%. Very, very small. Okay? Okay, so all of this was the background, right? Showing you what happens when we have a distribution. This is back from like chapter 7 and 8, and we get a t distribution and figuring this out. Let's go back to the actual work you would write down back on our problem. And it's basically the last half over there. Let's get back over here. So we are starting with our null hypothesis, alternative hypothesis, our sample information. The next thing you have to do is write down your test statistic. Test statistic. The test statistic is this formula right here. It is that t sub naught is equal to x bar minus, well, did they put a, they probably put a mu sub 0 over sigma sub 0 over the square root of n. Let me double check if that's the way they wrote it. Oh, they wrote s. There it is. So that's the formula you're going to get on your test. X bar minus mu sub 0 all over s over the square root of n. So it is s. We got it from our sample information. That makes sense. Write that as an s here. S. Okay. So that formula is exactly this thing. It's this guy right here. Right? So we got this as s. Here is x bar minus mu sub naught, the mean from our assumption. Right? That came from this guy, which we assumed to be true. And then s is our sample over there. So that little test statistic formula is just going to produce this guy. And then from there, you know that in order to get the proportion that you're really interested in, all you have to do is this guy. Right, so I'm basically going to recopy this part of the board over here, and that's part of what you have to do on your answer for over here. Back to this guy, we have our test statistic right there, so then we find it. T naught is equal to x bar, which is 128.7, minus mu sub naught, which is 154.8, divided by s, which is 46.5, divided by the square root of 50. So you do that, and then you find that T naught is equal to negative 3 point something, right? What was it? 969. And then from that, this is our test statistic, and now we find the p-value. So we write down our t distribution. with degrees of freedom equal to 49. These are little t values. The mean is 0. The mean is 0, sigma is equal to 1. And we have a value over here of negative 3.969. That's pretty far off. It's almost 4 standard deviations to the left. So we know that's really far off to the left. And now we find our p-value. Our p-value is going to be equal to probability that t is less than negative 3.969, which is going to be TCDF from negative infinity up through negative 3.969, comma, 49 degrees of freedom. And this is where we found that the answer was 0.000111778. And then, of course, if we want to round to 4 significant values, we would leave it there. 0.0001178. And that's pretty small, right? That's way smaller than even 1%. So that's pretty small. And now we compare it to alpha. That's our last step. Compare alpha to the p-value. So if the p-value, well, I'm not going to write that this time. I'm just going to write down the one I need. So we found that in fact it's smaller than it, right? So because p-value, which is equal to 0.00011778, is less than alpha, which is given to you in every word problem. Does anybody remember catching what it was in this case?
0.05.
It was 0.05 in this case as well?
Yeah.
Okay. So it's less than the given alpha value of 0.05. Because this is true, we do have enough evidence to reject it. Okay? We reject the null hypothesis. We reject the null hypothesis in favor of the alternative. Okay, so what is this mean in terms of our work problem? Well, it means that we do have statistical evidence to support that internet users watch less television than non-internet users. Okay, we have statistical evidence to support. We have statistical evidence to indicate or support that internet users watch less TV. The mean hours spent watching television by the mean hours spent watching TV by internet users is less than non-internet users. The internet users do watch less television, according to our data. Any questions about this? Right, so just this part is what I would expect to be written. Null hypothesis, alternative hypothesis, the sample information. This is given to you, so you don't have to memorize this, but you have to know which one to use. You're going to have a big formula sheet with lots of stuff on there, so you have to know where to go and which one to use. So that'll be given. Then you have to write this down. This is what I consider showing your work. You're showing me which formula you used and which values you plugged in. So this you don't have to write down, but this you do have to write down. And then give me what that answer is. Then I want a nice little picture showing me what area we're talking about. Remember that when you put this guy in here, the fact that it goes to the left is guided by two things. It's always that or more extreme, so that's why I knew it's that way and not this way. But also based on this, right? See, it's less than. We're doing a left tail test. This one's called a left tail test. Left tail test. Okay. So we find that area. So the p-value is going to be the likelihood of getting that result, that one right there. So we need to write this down. The probability that t is less than negative 3.969. Now you can use this, or if you want to write it back down as x bar, that's okay. If you want to write down the probability, so this one, or say that the probability that x bar is less than 128.7, I would accept that as well. So this is what the one we really wanted to know. What's the likelihood that the mean result would be less than 128.7? Well, that's equivalent to finding out this t distribution value. Probability that t is less than negative 3.969. TCDF, negative infinity, 3.99. Okay, so we have to write that down. Write that down. And then some sort of a little statement like this and a little conclusion indicating what your results are. Any questions? Questions? No? We're good? Okay, so let me give you your test back, but I have to just record them real quick. Stop this guy.